Hello, my name is Mieka Clark,
And I am Liam McLeod.
and we are presenting on behalf of the Amazon Die-Cast Aluminum team for this year's Design Expo. Our sponsor is David Peters from Amazon Lab 126, and our advisor is Dr. Paul Sanders from the Department of Materials Science and Engineering. Amazon requires a die-castable alloy for use in consumer electronics such as the Halo Fitness Band and Kindle Oasis, shown on the left and right respectively. Moving to die casting is not only more economical, but environmentally friendly than current production methods. Casting requires 25 to 40% less energy than machining raw parts and produces less scrap material. Various requirements for the application of this alloy are a yield strength of 120 megapascals, an elongation of 2 to 5%, an ability to produce thin-walled castings, a resistance to corrosion, and most importantly, an ability to be anodized.
Many alloys currently used for die casting contain silicon. Aluminum silicon phases in these alloys are unable to form anodic layers, shown as the white spots on this anodized A356 sample. It was hypothesized that if alloy composition and solidification rate are optimized, then the anodization quality will be improved because the surface of the casting will be single phase. This can be shown with the Schau solidification model of Al3Mg2Si, where the first to freeze region is seen to be single phase aluminum.
In order to test this hypothesis, 3 alloys were selected for casting. A360 is Amazon's incumbent alloy, while Al3Mg2Si and Al5Mg were chosen for varying silicon and magnesium contents. To cast the alloy compositions, a gray iron coat and sand drag were used in combination to make a semi-permanent mold. A tree mold allowed for casting thicknesses from 0.5 to 5 millimeters. From the resulting castings, the length of each branch was measured and recorded as a percent of the total branch length. Filling capacity was found to be comparable across alloys, but decreased with cross-section. Yield strengths were below the desired 120 MPa requirement for all alloys, though elongation was adequate, above 2%.
After tensile testing of the alloys, small sections from each casting were anodized. This was done using a sodium hydroxide etching bath and a nitric acid wash to thoroughly clean the surface of the samples. Each sample was then submerged into a 1.25% fluoroboric acid solution. A voltage was applied over the aluminum and platinum plated cage to build the anodic layer. Each sample's anodic layer was assessed through optical microscopy. It was seen that Al5Mg formed a nearly continuous layer, while Al3Mg2Si formed a decently thick but discontinuous layer. A360 formed almost no anodic layer whatsoever. From line counting of breaks in the anodic layer on the previous images, it was seen that there was a statistically significant difference between the alloys in terms of anodic layer continuity. Al5Mg was seen to have the least amount of breaks in its layer.
Given its sufficient elongation, improved anodizing performance, and comparable filling capacity, it was seen that of the 3 alloys tested, Al5Mg is the best suited for future anodization applications if its strength can be improved.